because it's showing the title of the next slide. Yeah. Okay. Okay. Well, let me use the. That's why I always have the backup of using the PDF. Yeah. That's good. That's good. And that's okay. Well, first of all, I mean, traditionally, thanking everybody. You know, it's repeated every year. It's a repeated pleasure to come to this city. And knowing, especially this year, all the efforts that have been made by the organizers to be able to do it, because there was, for instance, another conference in March that had to be cancelled because of budget restrictions in this country. So a big acknowledgement for everybody for being able to organize this conference, and once again, and especially to Georges and all his team. This polymodels, which also, you know, in terms of, it's a whole framework. It's not the first time, it's probably the third or fourth time that I'm talking of this here, talking in different places. So in some sense, I'm repeating myself, and in some sense, I'm trying to make it more precise every time I'm repeating it, and go deeper into the theory. It's a different way of doing factor analysis. You may find it, you know, a bit awkward in finance. You have to know that when I see in other disciplines, the first time I got, you know, the idea of this theory was when I was reading a book on genetic analysis, and it was the problem of identifying genes on a big piece of DNA. Then I noticed, talking recently with people doing all those marketing analysis, you know, that's big data, what they call, you know, the identifying behavior of people for, you know, those big companies like Google, etc. The type of technique that they use is very close to what I'm doing here. So basically, you're in a very complex world, and I don't think finance is an easy one. And we want to understand the behavior of assets. So let's see, you know, what are the questions. So, of course, the benchmark is the traditional multi-factor analysis of an asset. So what is, you know, you have an asset which I call Y. In statistics, you call it a dependent variable. Then you have independent variables that explain the asset. And you try to find a function, f of x1, xn, such that y is f of x1, xn, plus some noise that is supposedly independent from the x, y. So you'd like, I mean, another way is kind of a conditional expectation that you try to estimate. And I listed, you know, the traditional questions that are addressed in many of the academic papers. The distribution of the residuals, the quality of the fit, so how spurious it is, the p-value problem, etc. The convergence of the estimators, so the f is parametric, non-parametric, how do you converge to the correct f given data? The relevance of variables, whether, you know, we could reduce or augment the set of independent variables. And these are, you know, all those questions that are always asked in academic papers, and you see zillions of papers, you know, that will tell you, well, you know, I'm analyzing that, and here's the relevance of this, and I should apply, I'm using a dummy variable, and blah, blah, blah. Let's switch to the real problems, which are not exactly the same. I just listed, and when people tell me real problems, yeah, but it's not mathematics. Well, as you see, I try to make a mathematical formulation. Of course, real problems cannot easily be formulated in math, but I try to make a mathematical formulation of those real problems, just to show that it's possible to ask mathematical questions that come from reality and that are not, the thing that you see in the literature. So, first thing is, what are the source of risks? When in any decision in life, from crossing a street, taking a plane, taking a job, protecting your children, whatever, before measuring a risk, you want to know where it comes from. Because if you don't understand where it comes from, you have absolutely no clue of how you're going to measure it. So the questions are, what are the variables that matter? And the variable that matter is not a variable that matters in any-day life. You don't care that the pilot of the plane, when you're entering a plane, has, scratching on his back. But you care whether the guy has a serious physical problem or a serious psychological problem, whatever. You care about the extreme. You don't care about, the middle thing. Because that's what is putting your life at stake. The rest will have no influence. So the question are variables, the relevance of variables when it matters. And the second question is, once a variable matters, which means that there is some joint behavior. Forget about the word correlation. For me, the word correlation is a very broad word, but I noticed that most of people, for them, correlation is a formula in Excel. So you want to know, what is the influence of a given variable on your asset only on the extremes. So you want to have, in some sense, the asymptotic behavior. What is the impact of every single point in the S&P, provided it moves more than 5–10%. And below that, doesn't matter. Second thing, so how far can it go? How frequently? Here is, I'm not talking, in the previous sentence I said how far they go, that I mean that the risk factors. In here, how can it go is actually the asset. So what is, in the end, the distribution? But in here again, distinguish between statistics of observed data and the future. If I'm asking you what's your anticipation, I mean, some of you live in the US, they have 401ks, they have to design their portfolio for their 401k. They are engaged over a number of years. So either you trust the guy who is managing that. Well, it's not my case because I know them. So you make bets based on different assumptions on how you are going to manage. I know that on the one hand, I don't trust them. On the other hand, I'm very lazy. I'm not going to actively manage my portfolio. So I'd better choose something that I'm not going to change every day. On the other hand, I want to use not the statistics, but my estimate, my own estimate, taking my own risk of how the market is going to move with all the possible information I have currently. So what's the return distribution in the future, taking all the available information? Second thing, can I anticipate dangerous events? In some sense, if a crisis is coming, do I have some type of thermometer that will tell me, well, the times are hot or the times are quiet, like you have with the weather forecasts, every people who is sailing, who is going to the mountain, the first thing they do is weather forecast. And the last big question is about diversification. Diversification is the joint behavior of assets. And again, in here, why do you need the joint behavior of assets? I don't need a copula. I mean, copula is one approach. I'm not rejecting it. I'm just saying it's one approach. The thing I'm not interested in is not the joint behavior. The thing is that I'm interested in is, given any combination, what is the distribution of that combination? In other words, what is the core distribution, what is the expectation, and what are the tails? So this is, so when you see all those questions, and you find out that you can ask mathematical questions about all that. They're just not the questions that were asked in the previous slides. But, so this is where I'm going to show that nothing is perfect in statistics, but at least this polymodal approach gives better answers to all those questions. Oops. Why, before saying I have a solution, I mean, the first thing is, why aren't we satisfied with the existing solutions? Multi-factor analysis, what are the problems with it? Regime changes are the first major reason for the problems in using all those multi-factor models. Basically, we all know we have fat tails, etc. Actually, Bruno gave a very good talk on that topic, you know, comparing the third moments and looking, you know, at the impact of changing volatility versus a true third moment question on different assets. And in here, yeah, you find out that most of the reasons for fat tails are due to the fact that the volatility is changing, that as soon as you use a certain horizon, you'll face different regimes and therefore a mix of distribution. Each of them could be considered as Gaussian, but in the end, because of that mix, you get fat tails. The problem in here is I like looking at, you know, this conditional prediction. What is a conditional prediction? That you assume that you know the factors in the future, but the transfer function from factors to the asset, this one has been calibrated with available information at date t. So it's like you calibrate a model, you compute the factor loadings at a given date, and then you use the information in the future of the risk factors, and you compare that to the actual values. So the hat is the prediction, the yt+1 is the actual value, and what would be an R square? An R square would be the same thing in sample. It's a variance of this would be the residual. So it would be 1 minus variance of residual divided by variance of the source. That's the R square. Here, that's why I'm calling the P square. It's the prediction power. And I'm not predicting far away. I'm just predicting the next step. I'm recalibrating every time. So you take now a time series. You take your factors. Every time you take a sliding window. You recalibrate every time your model. You just look at the next step. So I'm not doing like in medicine where I cut, you know, my population into a sample, into a test sample and a calibrating sample and a test sample. That's completely independent. In here, I'm not doing half and half. I'm just taking, you know, just the next step, and I'm using information until the previous time period to calibrate. So this residual, you know, I get a lot of information to compute it. And I compute P2, but P2, there is no reason why this should be less than that. And in fact, when you compute it, it's very often negative. What does that mean? That this is kind of independent from that. And so the variance is the sum of the two variances. And then you find out that it's minus the variance of this one. So the prediction power cannot even compensate for the correlation between the hat and the non-hat, doesn't even compensate for that the variance of the residual is bigger than the variance of the source. Test it, you'll find it's pretty often the case. Why is it so? Essentially, problem of rigidity of the model, which stems from the linearity. If you put too many factors, then you get an overfitting problem, and you get also instabilities due to the collinearity of factors. Second question. Sometimes it's okay, and this is not too negative. But it turns negative precisely when you need it. Why so? Very simple. You need it precisely. Basically, the use of a risk model is when you have a crisis. A crisis means a regime change. Regime change means what you have calibrated is no longer valid. The third thing is, because of that, you compute correlations between assets, and then you find out that those correlations are not relevant, again, when you need it. So you have, you feel like you're diversified. That was exactly what occurred with hedge funds in the crisis. Hedge funds were apparently uncorrelated to markets, but when there was a big market event, they turned out to fall together with the markets. So they turned out to be correlated. I like this slide. It's not the first time you see it. An optimizer is something that maximizes the ratio between expected returns and risk, but in fact it's not the risk. It's just the risk as measured by the optimizer, whatever you use, including polymodels. We'll see that. But I'm being very general in here. Of course, reality always has hidden risks. So when you optimize, you try to increase the green, which is usually difficult. So you try essentially to reduce the red. So you reduce the red. But by reducing the red, in fact, either you keep this one constant, and even in something, quite often you increase it, not even you keep it constant. And so that the first result of an optimizer is not to make your portfolio better, is to put even more dust under the carpet. And I can show it again mathematically. It's not, like our experience, real life, math don't work. No, on the contrary. It's a mathematical fact. Suppose that you have, a certain number of assets, Y1, Ym, and that the distribution of those assets is a mix of different distributions. So pi are the probabilities, and those big P's are the different regimes. Now, an optimizer typically will take, I sort them out by bigger probability to smaller probability. And an optimizer will typically take, the biggest models, the first one or, the first 2-3 models, and will try to optimize according to those models and ignore the small ones that are just out of the model. So what happens is that you take a portfolio and you find a combination such that the risk under P1, P2, etc. is reduced. Now, the fact is, the tails, suppose that each of those models doesn't have such big fat tails, but the tails come from the combination of those. So you get those low probability model, but with typically higher standard deviation. So what happens is that the tails come from the ratio between the standard deviation. If you have, some like a 1% or 5% probability model that have a standard deviation which is 2 or 3 times, that's not such a big fat tail. But if you have that, low probability model that have standard deviation that's 20 times, yes, here you have a real fat tail. You see? That's how you create the fat tails, essentially, is how far you go when the probability decays. And what happens when you do an optimizer based on the major regimes is that you reduce the risk of the major regimes. But by reducing the risk of the major regime, because the other regimes have different specification, different correlations, you tend not only to keep them on the other, but you tend to increase the risk on the others. So you massively increase the ratio between the standard deviation according to the first model and standard deviation according to the last model. So that's why your optimized portfolio has much fatter tails than the unoptimized one. This is, when you think those regime changes, it's just obvious. So now the data wall, when you want to calibrate models, especially multi-factor models, is the fact that the range of possible models is enormous. You have lots of assets to calibrate. Each asset has a time series that is not so long usually. You have tens of thousands of risk factors against which you can explain them. And so you have, for every single asset, too little information and way too many possibilities to model it. And probably they are not totally irrelevant, but certainly you cannot say this asset is this model. So that's where, yeah, this one you've seen it many times, so I like it. So what the principle of polymodels is precisely saying, I don't know how I'm going to explain that. Oh, was another typical example of polymodels is handwriting recognition. All the algorithms that do handwriting recognition, they see a shape somewhere, on the paper, and they don't tell you, oh, this I recognize an A here, I recognize a B here, etc. They just tell you, I'm not sure what letter it is, but it looks like more an A than a B. It's all comparative. And very often, it's very fuzzy. Sometimes it's very clear. But it has a dictionary of possible models. And if I were to choose, I would choose, I'm not sure whether it's an A or a V reverse or something like this, but it looks like those, and it's certainly not a Q and not an S. So it scans the different models. That's the same thing we're going to do here. So I'm not saying that the asset is fully explained by X1 or fully explained by Xn, but I say if I were to explain it by X1, here's what I would get. So I'm looking at, I use sometimes this language. I say, the function of n variables is like a risk surface, and this one is a risk curve because it depends only on one variable. So taken individually, each model is quite imprecise. However, when you take the full book, then you get a very accurate description of a given asset. And that's what we are going to leverage on. So the whole idea is to try to see whether the list of questions that I was asking at the beginning will be answered in a better manner by this approach, assuming that I get all this information. In terms of memory, well, it's nothing with today's computers, because you have a few tens of assets, a few hundreds of factors. So that's a few hundreds of search models. Each model, of course, has a few parameters because you are going to use it. Altogether, it's no less, no more than any type of Monte Carlo representation. And, the second thing, which is pretty interesting when you do this thing, is that the factors are, you look at them independently one after the other. You don't care if they're correlated. It's like in the alphabet. Okay, if you recognize an O, you will certainly recognize a Q as well. And then at some point you have to go very deeply to identify whether it's an O or a Q. But you'll see that there is some round somewhere at first. In here, same thing. If you identify that there is a relation with the S&P, there is very likely a relation with a lot of factors that are highly correlated with the S&P, starting with all these sector indices, values, growth index, etc. So, of course, you will get, but you will get slight differences. A better fit with this factor, etc. So, in this type of theory, you are not afraid of using many, many factors. Even though the factors are related, are correlated, and even are linearly dependent. You can mechanically take one factor, another factor, the spread between the two, the combination of the two, and then you get, different. Geometrically, think of it this way. You have a random variable somewhere. What is multi-factor analysis? It's taking different directions, taking the span, so within the space of random variable, you are taking a finite dimensional subspace, and then you are trying to project that random variable onto that subspace. So to find the random variable within the subspace, which is the closest to your initial random variable. This is what you do when you do multi-factor analysis. In here, instead of having one span, which is finite dimensional, you get, you throw lines. Not even lines because they are nonlinear, so they are small dimensional, but they depend only on one random variable. So it's 3, 4 dimensions, depending on the number of parameters that you have in your nonlinear model. But you're throwing a lot of them. So basically, it's like comparing a Galerkin technique where you approach a function by a parametric function to a Monte Carlo where within the space of random variables, you throw all those risk factors and you try to find, it's like a triangulation problem, like exactly the problem of the GPS problem. You say, oh, if I project onto this one, I get there. Here's my distance. So if I project onto that one, I get there, and here's my distance. And from that set of projections, you try to identify where you stand and answer all those behavior information of the random variable with respect to those different, to the set of projections. So all those conditional expectations that compute here are all the set of projections of your random variable onto those different explanations that you have. So, to show you a typical usage of such an approach, you take this asset and you want to know whether you are going to invest. So you look at it, and the statistics look absolutely fantastic. Nice sharp, low volatility. The VAR is even lower than the volatility. The peak to valley is nothing. The skew is positive, no kurtosis. It's, of course, very nice, and you like it, and there is no fat tail, and no surprise, of course. There is no surprise. Yes, there is surprises. So the question, is it possible from the black line to anticipate the red? Well, the way I stated the question is a prediction problem, which, as we know, like promises, predictions engage only those who believe in it. The risk problem is not to anticipate the red line. The risk problem is to anticipate the possibility of the red line. You see, when you look at that, you are not saying the red line will or will not occur. You are implicitly saying it cannot occur because it's out of the statistics. Well, the last time I saw a curve like this that was, really predictable and that the red would really, I did not believe the red could occur, is when I saw the unemployment curve in France. It looks like that, but except that you don't have the red, except in the Holland speeches. So how do you anticipate that? Well, in fact, the idea is to say, if there is a growth in the black part, it has an explanation. Let's try to find it. Well, I can tell you how I generated it. It's an artificial fund, which is very simple to do. You invest in a AAA corporate bond. You adjust the duration so that it stays at 10 years every month. And you sell a T-bond with the same duration. So you strip out the direct interest rate risk and you stay with the AAA spread risk. So, of course, the relation between the fund and the actual AAA spread is not exactly linear, although it's close to. But if you use the long-term history of the AAA spread and you look at that as an explanation, it's like, this X1 or blah, blah, blah. Well, you find out that this event is big, certainly, and completely unrelated with the black part. However, in the past, there has been events that were in the same order of magnitude. Yeah. Oh. Okay, so let's go fast. So, I'm showing you, how do you measure risk with polymodels? Basically, the most important thing is you select factors. You select what I call the dominant factors. That is, the factors that have a given p-value. So you have to put a test. I put a test, which is some power less than 1 of the best explanation. And it's like, when I was saying, sometimes it's a clear case that you have a letter which really gives you the letter. So you will explore similar letters. But in some cases, it's so unclear that you are going to lower your threshold and accept a lot of further explanations. So the degree at which you accept or reject a factor will depend on how you select it, and it's on a case-by-case basis, so you have to put a rule. And then you measure the risk by saying, like I just showed, you take a very long history of the risk factors going through different crises, and you take the worst impact as a single factor, what I call stress value at risk. And globally speaking, you say the risk is the worst case that I can get from all those factors that potentially explain the risk of my fund. So you at least answer the question of what can potentially happen to your investment, what can and not only potentially happen to it, but also you get the explanation for it. So you know the risk source of that risk. I'm going fast. So relation between polymodels and multi-factor. I made it in the linear case, and you'll find out that, you know, if you can write a multi-factor model this way. A polymodel, you know, will have a series of such writings here. And you can go from one to the other by simply inverting a covariance matrix. I'm missing, I think I made a typo here. I forgot it's lambda is covariance matrix -1, apply not to betas, but to beta times variance of each one. But basically, you see a relation between the multi-factor models and the nonlinear and the single factor models by inverting the correlation, the covariance matrix. Here, you notice that precisely if you cannot invert the covariance matrix, you get a collinearity problem, and you find out that, of course, the multi-factor model cannot be calibrated. Well, I pass on that theorem that's, you know, that gives you the nonlinear case of, you know, in which case you can go again from the single factor models to the multi-factor model. That's a paper with a theorem we did with Alexander Cherny. The second question is, what happens to my phone if I have a given scenario on the factors? Here I get a problem that we call sensor fusion problem. So I know that the first risk factor is going to, you make some assumption that, you know, S&P is moving 5%. Interest rate are shifting 100 BPs, etc. Credit spread are doing so and so. And you get all those explanations. And they contradict each other. Whereas in a multi-factor setting, it's easy because you put your value into the factors and you know what they are doing. In here, you get a problem because they are contradictory. So you have to make a choice or to use the previous path from polymodels to multi-factor models. But this path is not safe because we saw that we have to invert the covariance matrix. So the idea is that we'll optimize that. How do we optimize? We compute an information ratio which is equal to the size of the impact versus the global expectation divided by the uncertainty on the impact. And that uncertainty on the impact is measured. I know Nicole made a comment to me by saying, okay, you use Gaussian assumption to you do whatever. I mean, you can, the idea is here, to measure the uncertainty on the impact, you have to measure the uncertainty on the calibration process that you are doing to get the impact. So essentially, it comes from the Fisher information matrix on the coefficients of the polymodel. And you see that for every single factor or subset of factors, if it's a single factor, you get, you know, you calibrate the model, you get some uncertainty on the coefficients, then you say, I want to move the factor to a certain level, therefore that prediction has a certain uncertainty, and I get, you know, the ratio between the impact and the uncertainty. If you have several factors, you can merge them, use the previous relation between single factor models and multi-factors. You increase probably the uncertainty. In some cases, because you get a better explanation, you increase the impact, and you get a different information ratio. Altogether, you try to pick either the single factor or the small combination of factors that have the best information ratio, and you call that the prediction. So I will go fast on those and show you on a set of hedge funds how you predict the crisis, the 2008 crisis. So this is, again, you know, this is a Y hat that I showed you, and this is a Y. So it's actually actual performance over September 2008 after calibrating everything as of August 2008. So this was a famous 7-factor Foncier, etc. The dark dots are actual hedge funds. The pink ones are funds of hedge funds, so already combination of funds. And the yellow ones are hedge fund indices from HFR. The blue line here would be a perfect prediction. And you see that on the right-hand side, you do some job. On the left-hand side, you are completely off. That is, you absolutely do not predict the actual losses. Now, if you use a polymodel, here's what you get. It works well because it is a crisis. The correlation is 90%. The R-square is 0.81. It works well because it is a crisis. Why so? Because in a crisis, suddenly, everything becomes very correlated, and so you get an extraordinary explanation. In other cases, you would have to, the distinction would not be so clear. So in some sense, the polymodels, they are the reverse from multi-factor models. They work only when you need them. They don't work otherwise. Yeah. This one is interesting because it's a prediction of the S&P with respect to economic factors such as growth, inflation, interest rate, currency basket, etc., real estate. So again, here I'm using with quarterly data this is using annual data. So each dot here represents over the years, it goes from the 60s, and that the yearly performance of the S&P versus economic facts. So if you have a model that gives you anticipation of economic indicators, then you get something that gives you a good prediction of the actual behavior of the stock market. So it tells you when you should invest or not in the stock market. For long-term investors, it can have some influence. The last thing which is interesting is how do you build a portfolio. So that's my last point here. So again, getting the polymodel for a portfolio is quite easy because you just combine the polymodel. So every single model with respect to each factor, you make a combination and get the model. The only question here is the relevance. In order to get the relevance, you need to get some ratio between. The relevance is always a function of the ratio of some risk measures between. It's not just the variance, but it's a ratio of risk measures between the residuals and the explained part. It always comes down to that. So you need to get some estimates. And in here, at some point, you need to get a risk measure of the residuals. And for that, usually people use correlations, etc. Here, I don't like the correlation of time series because they are unstable, they are irrelevant, they change, etc. But you have something much better than correlation of time series. Because you have a polymodel, you have each of those variables, they have a sequence of explanations. So you get correlation not of the time series, but of the impact of the risk factors. You get a huge vector of impact of risk factors, plus weights which correspond to the relevance, typically minus log of the p-value. So you get those correlations, and using that, you start having something that is stable and that's reliable to compute so I won't go into the details of the algorithm, which is a bit complex in here, but just to show you the impact. So using the dominant factor technique, this is, so here what the game that we did. You take 3,000 hedge funds, and you have a portfolio construction technique by risk budgeting, essentially. So you use the correlation. You try it's a risk parity portfolio construction technique. So you just make even all the contribution of the different funds to the portfolio. Instead of doing that on a big portfolio of 3,000 funds, what you do is that you pick at random 100 funds out of 3,000, and you do this optimization within 100 funds. So of course you get, for every subset of 100 funds, you get a different performance. So that's why you get error bars, because you get a distribution of such results. So we compared, this is just investing in cash. This is, this one is a dark one. It's a risk allocation. So you just, in each fund, you invest 1 over volatility. The blue line is equal investment in all the funds regardless of the risk. The green line is computing a Markowitz optimization simply using observed volatility, correlation, and performance. And the orange one is using the polymodal technique. And you see that it's doing as good as a Markowitz optimization when the market is bullish, but when you have the crisis, it resists to it, including the error bars. I'm going fast on classifications of hedge funds. So this is a very simple thing that I did, taking all the hedge fund and investing in 1 over the volatility of the fund at every time, and sorting out the funds with a negative Sharpe ratio, the green line, a Sharpe ratio between 0 and 1, the blue line, and the Sharpe ratio above 1, that is, you systematically invest in the very good managers. And you make no better than the average as long as the market is good. You lose exactly as much during the crisis, but when it comes back, you just miss the recovery. If you use polymodels to do that, here's what you get. So just to show you, the efficiency of this technique again, where you resist a crisis and you get it back. That I will go fast. And in here, it's the same thing done with ETFs. So this is very liquid. This is actual trading strategy, tradable, very tradable. And so again, so this is using, very conservative parameters for the portfolio. And you get here, I'm very focused on the Kalmar ratio, which is a ratio between the performance and the maximum drawdown. And the Kalmar ratio in all cases is above 1. So this is more like almost 2. This is about 5% performance for 2% drawdown. This is more like 8% performance and 8% drawdown, and 7% drawdown. And this is more like 16% performance. It's leveraged. And so this one is long only without any leverage. Thank you.
Okay, thank you very much.